in this lesson we are going to talk of a series combination of cells and find what is the equivalent EMF of this combination. Say you have these two cells which are joined in series with each other, and this is connected to an external resistance R. Now if you want to replace this combination of cells with a single cell, so we want to find what is the EMF of the cell with which this combination of cells can be replaced. Now you know that a cell also has an internal resistance. So say the EMF of this cell is E1, it also has an internal resistance which we'll denote by R1, and the second cell, let's say it has an EMF of E2, so it has an internal resistance of R2. Now for the cell that we want to find, the cell which is going to replace this combination, say that has an EMF which we'll call as E equivalent, and this has an internal resistance which we are going to call as R equivalent, and the rest of the circuit remains the same. You have the external resistance R to which this single cell will be connected. Now let's take a look at the current and the potential difference across these cells. See, you can see that, let's say a current I flows in this direction because this is the positive terminal. So you have a current that flows in this direction in the circuit. So the current I which flows through both the cells is the same. But if you take a look at the potential difference, then you have a potential drop across this cell which we'll call V1, and you have a potential drop across the other cell which we'll call V2. Now if you recall, when we studied resistors which are joined in series, we used the same approach. Say you have two resistors which are joined in series with each other. Now when a current flows through these resistors, the same current I is flowing through both the resistors R1 and R2. But if you take a look at the potential drop, then we have a potential across the first resistance which is V1 and across the second resistance which is V2, and the total potential across both these resistors is V1 plus V2. Similarly, in this case, the same current flows through both the cells, same current in both the cells, and the potential drops across them add up. So V adds up across both the cells. So now in this case I can write V equivalent would be V1 plus V2, and V equivalent is the potential drop across these two terminals. Say I call this 1, 2 and 3, then the potential drop across 1 and 3 is the potential across 1 and 2 plus the potential across 2 and 3. Now we want to replace these terminal potential differences with the EMF, since that is what we are looking for. We want to ultimately find the equivalent EMF. Now if you recall, V is equal to E minus IR. I have discussed this in the chapter, this concept in the chapter titled EMF and terminal potential difference. So if you want, you can just go back to that lesson, revise it, and then come back and learn this lesson further. Okay, now replacing V equivalent with E minus IR, we could write this as E equivalent minus I times R equivalent will be E1 minus I times R1 plus E2 minus I times R2. If you noticed, I used the same value of I since the current through both the cells is the same. Now you can equate the EMFs on the left hand side and the right hand side. So we would get E equivalent equal to E1 plus E2, and R equivalent would be, if I just take, I can just rearrange this and write this as E1 plus E2 minus I times R1 plus R2. So R equivalent would be R1 plus R2. Now this means that the equivalent EMF of this cell would be the sum of the EMFs of the two cells, and the equivalent resistance would also be the sum of the two resistances. So we have E equivalent equal to E1 plus E2 and R equivalent equal to R1 plus R2. Now say instead of just two cells, you had say 3, 4, 5, or I'll put it as n in general. So for n cells, if you have n cells, then we'll have the equivalent EMF as n times E. This is assuming that each of the cells have the same EMF E. And the equivalent resistance would be R1 plus R2 plus R3 up till Rn, and again assuming that all have the same internal resistance, this would be N times R. Now there's another important variation to this. See, in this case we have connected the terminals so that you have the negative terminal of the first cell connected to the positive terminal of the next cell. But we could also connect the cells like this, which means we connect the negative terminal of the first cell to the negative terminal of the next cell. So in this case, if I'm assuming that E1 is greater than E2, which means a current would flow in this direction, and through this cell it would flow from the positive terminal to the negative terminal, which means the cell with the greater EMF, since E1 is greater than E2, is able to drive a current through the cell with the smaller EMF. And in this case, the equivalent EMF is going to be E1 minus E2. Of course, if E2 was greater than E1, then the current would be reversed. So you would have a current in this direction if E2 was greater than E1, and the equivalent EMF would be E2 minus E1. See, if you look at the total internal resistance, we have a resistance R1 for this cell and R2 for the other cell. This is R1 and this is R2. So even in this case, the total equivalent resistance is R1 plus R2. And this was the equivalent EMF. So we can just summarize the equivalent EMF when the cells are connected in this manner, which means the negative terminals are connected together, is equal to E1 minus E2, and the equivalent resistance is still R1 plus R2. They don't get subtracted. There are 5 questions here to test your understanding. You have to choose the correct option. Here are the answers to the 5 questions, and don't forget to write your name in the comment box below if you've got all the questions right.